errors. So that's how do you get the mean drift? Well, the mean drift, or the trajectory, will take into account the temperature and the humidity for the 0 to 24 hours. I'm speaking about just one summer season. That for all days in the summer season, all hours in the day, matches as closely as possible the corresponding loads. Okay? So the load for a particular day and the hour. The difficulty with this problem is that it is an infinite dimensional optimization problem. Now everybody should be somewhat concerned by the word infinite. We don't have computers that accept infinite anything. They all have vectors of finite length. So now you have to come up with a method that's going to solve an infinite dimensional optimization problem. And the manner on which we rely is new development, which again I would like to talk about, but I don't have the time, or the audience isn't aimed at this particular issue, but it's a problem in approximation. Now people in approximations have been using spline piecewise polynomial approximation to functions because polynomials can be determined by a finite number of coefficients. If you take a polynomial of degree 3, you have 4 coefficients. And so you reduce the problem to a 4-dimensional problem, maybe of large size, but a 4-dimensional problem. So that's what we are going to do. We're going to solve that problem by developing a theory and numerics of episplines. It's a new theory of splines that are very popular for doing approximations, but these require something a little bit more sophisticated because you have to foresee the possibility of discontinuities, and actually the splines are a little bit too limited in including the possibility. The formulation of the spline problem is too limited when you include many pieces of outside information. And this is very important in our work. We, for example, can include any soft information, for example, the shape of the load, the expectation that the load at a certain time will be larger than this, and so on. And once we had developed this theory, so initially partially motivated by this work, we also applied it to various other applications. Similarly, we're now going to look at the volatility. And the volatility, since we do already now have an overall drift trajectory, we're going to look at the errors between our predicted load, which is this thing, and the actually observed load on each day and each hour in that subseason. And we will, for each hour in the subseason, actually find the distribution of the errors. And again, we are faced with this problem. We have 125 points. So we are not going to be able to use classical statistical methods. What we do is to actually complement the observed values by extrinsic or external information. It's again an infinite dimensional optimization problem, and the data again is scarce in order to work with that. Now, our volatility, our approach, instead of doing episplines, we use exponential episplines. The epispline is the exponential of a spline. It has the same properties. It can be solved in a finite dimensional way. And we can include all types of information that we may have. In particular here, what's important is that the distribution of the errors, or the distribution of the volatility, is going to be unimodal. That means that it's going up and then going to go down. Skewness, which means it goes more in one direction than another, and then whatever restriction we may have. Combining this, we get this. So our artistic view of what was possible is actually, we now realize that we get the distribution because for each hour we have obtained a distribution of the various trajectories that are possible. Again, this is not, oops. Now we do a little bit more of work. Now we're going to have to use this uncertainty distribution to solve a stochastic optimization problem. And people have two ways to deal with stochastic optimization problems. They say, okay, I'm going to sample the distribution. And for each sample, I will consider each possible sample, and there will be some probability associated with it, and I will then solve the corresponding problem. Or you can proceed by approximation. And actually, we decided to proceed by approximation. I see that in view of the time, I like to just give an idea of how we get some of the conditioning depending on the state of the system. For example, suppose that we actually split the day in a finite number of time intervals. And in order to not make it too difficult, I've only considered 3 time intervals in here. At 10 o'clock, we have a distribution around the overall trend. We then see if we are above or below the overall trend, and we look at all of the load that were above in order to get a new distribution of all of those loads who were above at 4 o'clock in the afternoon. For those who were below, we get another distribution which itself lies below the curve. And then we do repeat this operation again to obtain the distribution at 8 o'clock more richly, and we proceed in creating the process. To do this operation, we know one thing. I have been working in stochastic optimization a very long time in my life, and I know that what is important is not to work so much with the mean than to make sure that you catch the expensive cases, the cases that are sometimes called outliers, because those cases, when things go badly, you are close to a blackout, you are close to a brownout. In electricity terms, you're going to have to spend a lot of money buying on the spot market. And buying on the spot market practically bankrupt California at one time, or nearly bankrupt California a few years ago. They were obliged to go a lot on the spot market. So we divide in low events, events which have a low probability with probability below a certain level, and we split the distribution into maybe low, middle, and high. And instead of considering a full load of possibilities, we associate with each maybe 5-point conditional expectation of the discrete approximation. This allows us to reduce the process to a discrete process having a finite number of possibilities. So instead of the process that we started off with, we start off with a process which has now a discrete component corresponding. This can be viewed as a discretization of the other process. In the remaining minute, I will say a few things about wind and solar. The wind and solar problems, especially the wind one, are much more complicated than the load problem. But the technology that we use is similar. Okay? So here's certain days where you have the trajectory. The forecasts which are brought from a wind power provider are actually where the blue curves, and the red curves were the actuals which were observed. And if you look at all the possibilities, you see that on any one day you can get a lot of wind and you can get very little wind, and sometimes the wind is in the middle of the day when it's low, and sometimes it's the middle of the night, and every possibility. So just to make sure that everybody understands that many things are possible with wind power, I mapped all the wind power which was associated with 6 months. Okay, so there are 6 months, about 180 curves which lie in there, and you see that it is messy. Okay, but it's very important. Realize that the FERC, the regulations of the Federal Energy Commission, says you should use all the wind. So it's very important that they actually estimate the wind very well. Okay? Because if they don't get since they have to use it, they will then have to make, if they get a lot of wind, then they will make fewer contracts. Okay? They are able, this is essentially an independent contractor, but it's automatic. So we have to come up with a method. What we do is we follow more or less the same ideas than last time. We're going to look for a relationship between predictions and actual loads, actual amount of wind power. And we're going to try to create a trend, but this time it's no longer based on a subseason. What you have to try to use in this case is the soft information which comes from the drift, the dynamics of wind. It's the dynamics of wind that have to enter into it. And when we did this, we looked, for example, at when the wind drift, in this case, is of this form. And we will take a subseason consisting of, or sub-number of hours where the wind has this pattern. Similarly, here it looks at this subseason, sub-collection, and these are the hours that will be recorded. So there will be, for each one of these patterns, there will be a different type of dynamics that takes place, and we want to take that into account. And when we do, we get incredibly good predictions. So rather than estimating just in a natural way, which you learn in a statistics course, we actually use the soft information which comes from the dynamics of wind. So the wind scenarios are somewhat different from the way the loads go, because they actually, since you are making them about 12 hours before you start, you don't know how it will be at midnight. So you have more than one starting point, and they actually evolve over a certain number of time. As far as engineers are concerned, in order to check scenarios, they look at the energy score and the Breer score. And so far, the ones we have generated have been winning prizes because the energy scores and the Breer scores are the best possible. Now, I'm essentially finished my lecture. Now, once you have all of this information, you go to your optimization problem, choosing your contracts and spinning and so on, which are definitely. And